All right, so let's continue our discussion about the first law of thermodynamics. And specifically, we're going to talk about gases and continue our discussion of gases and what's going on. So I think I've gotten to a point now where I can get my phone up and running. So I'm going to go ahead and get the whiteboard back up here so that we can bounce to it. Oh, I got to turn myself off. Hold on. You'll get an echo otherwise. All right. So let's continue talking about gases, and I want to talk about specific heat. So where we've gotten, last time we talked about the different kinds of processes. So we had, things like isochloric, isochoric and isobaric and all that kind of stuff. And we talked about the first law of thermodynamics. Let me actually just put that back up here as a reminder. And basically what the first law of thermodynamics says is that the change in energy, it's actually comes from two places. It's either from heat, so we can change our internal energy by either giving or taking away heat, but then also work. So if we do work, we lose internal energy. If work is done on us, we gain it. Okay, so let's just remember this first law of thermodynamics because it's going to come into play when we move further. All right, so let me actually switch to the whiteboard view. I just realized I was pointing at the whiteboard, but people that are watching the video are going to be like, what the hell is he pointing to? Okay, so now the main screen is seeing the whiteboard. So the first law of thermodynamics, change in energy, it's your Q minus your W. And then the other thing that we saw, and this is for gases. For gases, it's easy to calculate the work. All it ends up being is an integral of Pdv. So if we know our pressure, and we can write it as a function of the volume, we just integrate that from our initial volume to our final volume, and that's how much work happens. So we did look at two specific cases, well, I guess three. If we were in the isochoric, so what's the same in isochoric? Because iso means same, but which was choric? What do we keep the same? I think I heard you say, Bradley, as volume, right? So this is where we have constant volume. And what we saw in that situation is that the work is equal to 0. No work is done. So if we keep the volume the same, it doesn't change. So that was isochoric. We also had isobaric. What stays the same there?
Pretty sure it's pressure.
It is pressure. Good. So that's constant pressure. So if the pressure is always the same, it turns out that the work done is just equal to the pressure times that change in volume. So if you keep the pressure the same, but you change the volume, the amount of work is just P times dV. And that's because on the graph of pressure versus volume, it's a horizontal line. So finding the area underneath was just base times height. Okay, so then the third process is where we keep temperature the same. So what's the name for that one? So good, Victor just put it on there, isothermic. So just remember thermometer, temperature. So isothermic means constant temperature. And that one we were able to calculate the work as well. But it actually made use of the ideal gas law, because we can write using the PV equals nRT. You can get P to be in terms of that. And so it ends up being nRT times the natural log of V final over V initial. So we calculated all of those last time, but that's how we can find the work in those three situations. All right, so that's where we were last time. But what I want to do today is I want to look at the heat capacity of gas. And specifically, we're going to start looking at this thing called gamma that we're going to need when it comes to adiabatic processes. And I'll remind you about that when we get there, but adiabatic, that just meant that there's no heat added, okay? But we'll get there in a minute. All right, so let's talk about specific heat, right, and heat capacity. So when we first talked about temperature and heat, and specific heat, heat capacity was a measure of change in temperature. All right, so here's what I want you to think about. Let's draw a graph of pressure versus volume. And let's talk about going from one point on here to another. And really, I want to go to a different temperature state. So what I'm going to draw here is an isotherm. Okay, and isotherms, those are lines of constant temperature. So if I were to find any point on this lower one, they all have the same temperature. Any point on the second line has the same temperature. It's higher than the temperature from the first line, but it's going to be the same anywhere on that line. So let's just call these, say, T1, T2, T3. So 3 different temperatures. And the way that I have it drawn, it's necessary that T1 is less than T2 is less than T3. Okay, so let's think about changing the temperature. So I'm going to start at this point that's at T1, and I want to increase its temperature. So basically, I just have to bring it to this other line in some way. Now, there are going to be 2 really easy ways to do this. The first is if I just go straight up. Okay, so that's going to be the first process that we look at. What kind is that? What name do we give that one? ISO what? All right, so Victor just put baric, isobaric. It's actually not isobaric because the pressure is changing. On these graphs, just to remind you, the vertical axis is P, the horizontal is T, or sorry, not T, V. So it's not isobaric because we are changing our pressure.
No. It's choric then.
Yeah, so this one's going to be isochoric. So I'm going to put a 1 here. So down below, we're going to say that 1, this is isochoric. So we'll look at what it does. Okay, so that's going to be one way we do it. The other way we're going to do it is if we move horizontally over to this point. So we'll label that one 2. And so this process is the isobaric, right? We've got the same pressure throughout. We're just increasing our volume. Okay, so these 2 different processes have to actually give us the same change in energy. Why?
Did you say same change in energy?
Yep, both of those are going to lead to the same change in internal energy.
Because the first law of thermodynamics suggests that energy is conserved. It doesn't. You can't lose energy from. I mean, you get what I'm trying to say? Like
Kind of.
the changes, no matter which way you do it, has to be the same.
Okay, and that is true, because it really what I'm getting at is temperature. Think about that temperature. These both end up at T2, and we know that temperature tells us exactly how much energy we have. So every point on this isotherm has the same internal energy. So when we go from temperature 1 to temperature 2, we have the same change in energy. Now, it's going to come from different places. Sometimes it's heat, sometimes it's work, sometimes it's both. But no matter what, if I start on T1 line and I end on the T2 isotherm, I'm going to have the same change in energy. So just remember, temperature is energy. The temperature tells you exactly how much energy you have. So if you're at the same temperature, you have the same internal energy for gases. Okay, so let's look at isochoric. And if we look at that change in energy, again, it's going to be Q plus W. And let's think about the heat and the work. So in terms of the heat, this is where we use specific heat. And you may remember from our discussion with gases that the heat that we add is N times C times delta T. Right? So when it was solid or liquid, it was mass times its specific heat capacity, right? But this one, since it's gas, it's number of moles times its heat capacity, its molar heat capacity. Okay, so that's our heat. And then what about our work? How much work is done in that? Good, Victor just put 0, right? So in isochoric, it's 0. All right, now I don't know if you remember, but when we first talked about heat capacity of gas, I didn't write just C. I wrote C sub V. And now you can see why, because that, we named it the molar heat capacity at constant volume. So that's what the sub V is telling you. So it's a molar heat capacity because it's a per mole, but it's when it's at a constant volume. So I just put that up last week and y'all smiled and nodded and went, okay. But now you can start seeing why, because in this process, yeah, we're going with the constant volume. All right, well, long story short, the change in energy on that path is NCV times delta T. All right, well now let's look at the isobaric. So we'll look at that second process. I'm just writing it a little bit higher so I can make use of the space. So this one's isobaric. Okay, so change in energy again is going to be Q plus W. Not plus, minus. Turns out it didn't matter with the 0, but it's going to matter now. Okay, so let's build heat. Heat, we're going to have the same thing, N times C times delta T, but this time I'm going to put a little P on that. So this is C sub P, so that this is the molar heat capacity at a constant pressure. So you may be asking yourself, why is he writing a separate C? Well, it's because they're not the same. we're going to see that they're not actually equal to each other. All right, so there's our pressure, or sorry, our heat. But now let's take away our work. So our work, in this case, since it's a constant pressure, it's going to be whatever that pressure is times the change in volume. Right, whatever those guys happen to be.
I have a quick question.
Yeah.
I should know this, but I just want to be clear. Is a delta V the same as a dV?
A delta V is bigger than a dV. A dV is infinitesimally small. So literally it has no width.
Okay.
Where a delta V does.
Okay.
So if we want to go to calculus, we just turn the deltas into D's, and then that turns summations into integrals and so on.
Okay.
So they're similar, just technically a dV has no width.
Okay.
All right, now from our previous discussion, we know that these two changes in energy have to be equal because we're going from the same temperature to the same new temperature. So let's equate these. So we're going to have NCV times delta T. That's going to equal NCP times delta T minus P times delta V. Now we're going to go back to the ideal gas law one more time. Recall that PV is equal to nRT. And so if we want to look at a slight change in volume, this is going to be the same as Pdv equals nR times delta T. Now you may be asking yourself, why did we not put a delta on the P or the N or the R? And that's because all of those are constant. R is a constant always. N is the amount of gas we have, the number of moles. So we're assuming that we're not producing or losing any, so that's the same. And the pressure, remember in this case, that pressure was constant. Got it written right here. It's constant pressure. So it can't change either, it's just constant. Well, let's put that in for P times delta V. So we get N times CV times delta T equals N times CP times delta T minus N times R times delta T. And now we get to crack out our red slashing pen because there's an N in each of these. There's a delta T in each of these. And so what we find is that CV is equal to CP minus R. And I'm going to rewrite that because this is usually how you'll see it written, is that CP is equal to CV plus R. So these specific heats, these heat capacities, are not equal, but they're related to each other. Right? Again, this is for an ideal gas, which means in reality, it's not going to be quite this. It's not going to always be the same. But we should see that these two molar specific heats should be off by about R. And what's even better is that experimentally, we see that. If you go and you look for, look at this for certain gases, it's very close. It gets worse the more complex the gas is. the more complex the molecular structure is. So ones that are monatomic, right, like we were talking about helium, right, or some of the other noble gases, they're pretty much spot on. The diatomic are pretty close. So things like H2 or O2 or carbon monoxide. But the polyatomic, like carbon dioxide and things like that, they're not quite as close. And that's because they don't actually act like ideal gases. This derivation required ideal gas. And the more complex the molecule, the less ideal it is. Right? So it turns out that this is actually really, really close. Turns out that it's a pretty realistic number. The theory holds when you look at this experimentally. All right, so why do I bring this up? Well, if you want to do any kind of a thermodynamics problem with gases, where we're looking at taking heat and adding it and all that, we have to pay attention to what kind of process it is. If it's isochoric, use CV. Isobaric, use CP. If it's neither, you have to have some sort of combination of it. And unfortunately, it's not as easy as kind of what we do in calculus, where we just break it into components. We can't do that. And what I mean there, let me draw another graph. So again, we're going from one isotherm to another. And let's say we're going to go from here, but we're going to go in this direction. Now, I don't want you to write this. Do not write this. Because if we do this, that's not the same process. Okay, that is not the same process at all. So we definitely have to watch out for this. Really what you have to do is break this into little infinitesimal steps and do some calculus to it, because this is a different kind of route. Can you see why? Just in the discussion what we talked about last time. What's different about green and red? Think first law.
The amount of energy.
Okay, the total change in energy is the same because we're still going from this point to that point.
I don't think we've seen anything where you change pressure and volume simultaneously.
We have, like when we talked about something isothermal. But here was my next hint was going to be, so Jacob just eliminated one of the three things that are in the first law. So it's not energy. So there you go, Victor. How about work? The amount of work done on these two paths is different. How can I make that statement just like unequivocally? I know the work is different. And don't say because I'm the teacher. Because you should be able to tell me too.
Because of the change in pressure and volume?
No, not where I'm going. So Victor's kind of getting at it. Isochoric, so this bit, there's zero work. But how do you calculate work?
Force times displacement.
Okay, but for gases, how do we calculate work?
PV over T.
Okay, we're getting closer. It involves P and it does involve V, not so much T. I wrote it on the board not too long ago. It's the integral of Pdv. Kind of remember me writing that?
Yes.
Right? So think about the integrals along these paths. That's the area under these graphs. So which one of them requires more work?
The bottom.
So let's say areas. So here's the area under the green one. Here's the area under the red one. Right? So the red one actually does more work. And because it does more work, it's going to require more heat. Because if that change in energy is the same, either one of those paths, if the work increases on one, that means the heat has to increase on the other. So it's way more complicated when we take paths that are not isobaric or isochoric. But the reality is that happens way more frequently. So we do have to be careful. All right, we do have to be careful when we're doing these calculations. We have to watch out for these. Okay, but I will tell you this. Because if you go back and you look at what we were talking about last time when I just wrote C sub V and nobody questioned me about it, it does work out that if I were to do this path, I'm going to get the same heat, maybe not the same work, right? Or sorry, not same heat, the same change in energy as if I went straight up and hit this isotherm. So I don't want you to think, well, we're just screwed completely. But I can tell you this, that the change in energy, no matter what, it will always equal N times CV times delta T, even if we do one of these other paths. Because we know that that new temperature, that defines how much energy happens. And so we get it if we go straight up. So CV is the way more important number, because if all you want to do is figure out the change in energy, you can always calculate it this way. But what the balance is between work and heat, you don't know. And that's what's going to change. All right. So CV, CP, similar but different. The more important one is CV. But the other thing that's going to matter for us, that we're going to be interested in, is in the ratio of these. Okay, so the ratio of heat capacities. I'm going to use a gamma to represent it. That's just kind of the standard. But what it's equal to, by definition, is CP over CV. So given a gas, if you know it's CP, then you know it's CV, then you can figure out the gamma. Now, some things I want you to notice, I want you to see about this. First of all, first fun fact: gamma is always greater than 1. Do you see why? I'll give you a hint.
Because
CP is bigger, right? Victor just put that in. What were you about to say, Bradley? Sorry to cut you off.
I was thinking because either CP is going to be greater, and then you divide by a smaller number, you're going to get closer to 1 or greater than 1. And then if you have CP that's smaller, and then you divide by a larger number. Oh wait, never mind. That doesn't work.
No.
Never mind.
Well, the Y, just look right below, circled in red. CP is CV plus R. We always add R to get our CP. So by this fact, we know that CP has to be bigger than CV, and therefore this gamma is going to be greater than 1. It will get closer and closer to 1 as CV gets larger. As CV becomes a bigger number, then this is going to get closer to 1 because the difference in them isn't as great. All right, so let me just show you this. We calculated CVs, at least theoretically, what should happen for ideal gases. And we did this for monatomic and for diatomic. You remember the degree of freedom business, maybe? So here are just some things that we know. So for monatomic, we saw that CV was equal to 3/2 R, because that was the number of degrees of freedom. There were 3. There were the 3 spatial ways we could move this and see a difference. So check this out. If CV is 3/2 R, then CP is 3/2 R plus R, which is 5/2 R, which then means gamma is 5/2 R over 3/2, which is 5/3. So for a monatomic gas, in general, gamma is 5/3. This is pretty well matched experimentally, but that's what we see for monatomic. If we went to a diatomic, for that one, we had 5 degrees of freedom. You had the 3 lateral, and then 2 of the rotational. Remember the dumbbell? There was one way I rotated it that it didn't change, but the other 2 it did. So that's why it's 5/2. Okay, well then from that, we're going to get that CP is 7/2. And then if we take 7/2 divided by 5/2, we get gamma is equal to 7/5, or 1.4, which again matches experimental values pretty well. Now, you'll see what this gamma has to do with anything in a minute, but it's really this ratio that's kind of important. All right, so cool. All right, so we've got these 2 heat capacities. We now have the ratio, but why do we care? Well, let's go back to another process that I mentioned that we didn't really look into yet because we weren't ready. But let's look at adiabatic. So you may remember when we were talking about processes, I made a list of 4. This was the last one. And this one is harder to remember what it does because its naming isn't iso anything. But adiabatic, what this means is that there is no heat. All right, so Q is equal to 0. So in an adiabatic process, we don't have any heat put into the system. So yeah, Victor, that's right. No energy that's going in or out. Okay, so The only thing that's going to change the internal energy then is work that's either done by the gas or done to the gas, right? So if we go to the first law, you just go back to the first law, we're going to have that the change in energy is equal to the negative work.
Can you think of an example that puts work into a system without changing the heat, without, using heat? That'd be gravity.
Would gravity do it? That's a good question. Because, like, here's the thing, and I kind of thought this is where you're going to go with it, where you do work, but you don't change the temperature. But that's not what this is saying, right? Remember that change in energy, that actually is change in temperature. So in an adiabatic process, by definition, temperature changes.
Yeah.
Because all of the work is being put into changing the temperature of the gas.
Yeah.
Right. So these are usually things that happen if it's really well insulated. Right. So if you're insulated from your environment, you're not going to have heat transfer through, conduction and stuff like that. So it has to be really well insulated. And these processes tend to be really fast. So remember the paper towel that I lit on fire by just compressing that plunger?
Yeah.
That was a pretty adiabatic process.
Okay. Like combustion almost.
Because it was super fast. And so there wasn't time for that gas to lose heat to the environment. And so all of that work that I did by plunging down got turned into change in internal energy. So it increased the temperature.
Okay.
Right. So I think that's probably the best example I can give you that you've seen even.
Yeah.
That we could treat as adiabatic.
Okay.
Now, was it exactly adiabatic? Probably not. Right. There was going to be some heat loss to the outside, but not a lot. At least not to the point of when we set it on fire. After it burned, right, then, all bets are off. Okay, so let's see if we can kind of derive what should happen if this is adiabatic. Okay, so let's turn this into a differential, because we're probably going to want to turn this into some calculus idea. So let's do these as little d's instead of deltas, even though it's really kind of the same thing. So we're going to just go with dE is going to be equal to the negative dW. So whatever small little change in the energy, it's going to come from the small amount of work that's done. Okay, now work, we already know, is a Pdv. So the differential amount of work is equal to P times the dV. And we also know that this change in energy is going to equal N times CV times delta T times dt. This was a fact that I put up just at the very end when I was talking about the two different C's and how CV is the more important one because it does tell you the change in energy. All right, so we're here. N, CV, those things are constant. But the P isn't. The P isn't constant, so let's get rid of it. Let's get it in terms of the letters in here. the V and the T? Well, again, ideal gas law to the rescue. So we've got PV equals nRT. So if I solve that for P, I'm going to get, again on the left side, NCV dt is going to equal negative nRT over V times dV. So let's simplify this a little bit. Let's get rid of the n's, because those don't matter. I'm going to rearrange this. So we get C, actually, I want dt over t. So I'll divide this t. And I'll actually move the CV to the other side. So we get minus R dV over V times CV. All right. And now let's integrate. Actually, no, before we integrate, let's get rid of that R. I don't want that R. I'm going to get it back in terms of CV and CP. So what we saw was that CP was equal to CV plus R. So we have the fact that R is the difference in those. So we're going to get dt over t is equal to negative Cp minus Cv over Cv times dV over V. So I'm going to divide that Cv in. So I get dt over t is equal to minus Cp over Cv minus 1 times dV over V. And here is that ratio of those heat capacities. That was that guy gamma. So I can rewrite this as dt over t equals negative gamma minus 1 dV over V. All right. Now I want to integrate, because this is going to be a little bit easier to integrate. So let's just take an integral of both sides. So what do you get when you integrate dt over t? So it's not just t, Victor. That's what we get if it was just dt. Like, what's the integral of 1 over x? There you go, natural log. So this is going to be the natural log of t. On the other side, the gamma is constant. It's just determined by the gas. So all of this is constant. So we're going to have negative gamma minus 1. And then when we integrate dV over V, well, we're going to get the same thing, natural log of V. But let's be good about it and put on our plus C. So really what I want to do is I want to get rid of those natural logs. So I'm going to use some rules of logs. Let's take this, bring it in as an exponent. So we get the natural log of t is equal to the natural log of v raised to the negative gamma minus 1. Since that's a negative power, I'm going to drop it to the bottom. So this is the natural log of 1 over v to the gamma minus 1. And now let's do an e. Okay, we'll take e to both sides. So this is going to give us t equals k times 1 over v to the gamma minus 1. And that k, it just equals e to the c. Because remember, an addition in an exponent is the same as multiplying outside of the exponent. And so c was an arbitrary constant, which means k is also an arbitrary constant. So we're almost where I want to be. I'm just going to do one more step. And so again, here's what we know about in an adiabatic process. We've got that t times v to the gamma minus 1 is constant. So this is why I cared about the gamma, because it kind of comes in here. But if we have an adiabatic process, whatever the temperature and volume changes are, they follow this relationship. So this is a conservation law, really, is that if there's a change in one of these, there's a resulting change in the others. So what you'll sometimes see this written as, maybe a better way of writing it, is if we go T1 times V1 to the gamma minus 1 equals T2 times V2 to the gamma minus 1. So I'm going to put a little box around that just so that we can remember that that's kind of a big deal. And so, hi, Max. Welcome. No worries that you're late. Glad you were able to make it.
Thank you.
You ended up, the first 45 minutes was not physics, so don't worry about it.
Oh, okay.
All right. So, beauty. This totally is true for adiabatic processes. So, go back to that plunger where we, actually, I got it right here. So, remember this, right? And I don't have any paper in it, so we're not going to see a big flash. But as I push down, the volume went from the entire volume of this tube down to probably about here. So the volume was now much lower. So there was a huge decrease in volume. And what we're going to do is see what that did to the temperature. All right, so we'll do that actually right now. Let's see if we can calculate what that change in temperature was. So we're going to need to know something. Well, we're going to have to make a guess about something, which is the gamma. What is the gamma of the gas that's in here? All right, so here was the example of the plunger starting a fire. Okay, so let's look at that. So first of all, let's decide on a gamma. So what do you guys know about the atmosphere? What makes up the atmosphere that we breathe? Do you know what the most prevalent thing is?
Nitrogen.
Yeah, it's nitrogen. It's like 70% nitrogen. Most people have no idea. Most people think there's a lot more oxygen in it. But it's like 70% nitrogen. There's also a fair amount of oxygen. And between those two, we can probably treat this gas, the gas that we're breathing, as diatomic. Okay, so that's what we're going to do. We're going to assume that it's diatomic. And if you don't remember, that gave us a gamma of 7/5. So we're going to use that as our roughly what happened. Now, in terms of the volume of this, I don't know. I have no idea. But we can make a pretty good guess on what portion of the initial volume do we have at the end. So we can relate V final and V initial. So here's what I'm going to do. Take my trusty ruler here, and I'm going to measure the entire height of the piston from the starting position, and then we'll measure the height of what remained once I compressed it. So this is ballpark. It's about 13 centimeters to start, and it's about 1 centimeter after. So assuming that the cross section doesn't change, which should be a good assumption because it's fairly circular. If it weren't, the piston wouldn't go down it very well. We're going to have the V final. Did I say it was 13 or 11? So V final is going to be 1/13 V initial. The initial temperature is room temp. And remember when we were doing all those labs, we were getting numbers around 26. But we can't use 26. Since we're using the ideal gas law, we have to use temperatures that are in Kelvin. So what is that in Kelvin? Do you remember your conversion?
Plus 273.15.
Yeah, so plus 273 puts us at 299. Let's just go with a nice number 300. It was a little bit warmer in here that day. Sure. Okay. So let's go 300 Kelvin. All right. So what we're looking for then is the final temperature, or T2. So let's put this all together and see what we get. So we've got T1, V1. So let's do, that's our initial. So we're going to have 300 times V initial to the 7/5 minus 1. That's going to equal whatever our final temperature was, times our final volume, which was V initial over 13, raised to that same 7/5 minus 1. So I don't know if you noticed this, but those initial volumes don't matter. They're going to go away. So we've got 300 is equal to T final over 13 to the 0.4. So T final is going to be 300 times 13 to the 0.4. So let's crack out our trusty TI-89. And let's see what temperature that gives us. All right, so I get just around 837. Now, that is Kelvin.
So 564 degrees Celsius.
So, yeah, so you take your 273 away from that. That's crazy hot, right? So, what did you say that was?
564.
564. So, just by plunging like that, I increased the temperature of that air to 564 Celsius. Crazy.
That's wild.
Right?
That's fucking wild.
I added 530 some Celsius.
Just by increasing pressure and decreasing volume. That's crazy.
Yep. And the fact that it was adiabatic. And
And
that
that's
would be
pretty
why
hot.
you saw that paper towel burst into flame. Right? I don't know what the actual flash point of paper is. I know like there's the Bradbury book, Fahrenheit 451. I don't know if that actually is the burning point of paper, but let's see what this is in Fahrenheit. So if we take 564 times 9 divided by 5 and then add 32. Oops. Okay, it's 1,047. So for those of us that are more Fahrenheit inclined, it was over 1,000 degrees. Yeah, that's going to burn paper.
That's a mind fuck, honestly.
I know, right? It's totally baffling to the mind, but the math suggests that it must be. Now, I don't know if you remember, but for polyatomic gases, the CV gets bigger. So that means gamma gets smaller. So it's not going to be quite this big in reality, but it's not that far off. It's really not that far off. Because remember that this whole thing, this adiabatic with ideal gases, this is sort of a perfect world where in the real world, it doesn't necessarily quite follow that. But definitely close enough. And again, that would be why you saw that paper towel erupt into flame. So, cool shit, huh? This is cool stuff. And this coming from the guy, I don't know if I told you I'm not a huge fan of thermodynamics. Did I tell you that?
No, you didn't.
It's one of my least favorite parts of physics, but even my least favorite parts are still freaking cool, man. So, all right. So adiabatic definitely follows this process. And again, think about that as if it's pretty well insulated, if it's very quick, those tend to be adiabatic. Now, we can change this a bit, and I want to show you a couple of different forms that this can take on. So this one involves temperature and volume, but we can actually not look at it as temperature and volume, but pressure and volume. If you go back to good old PV equals nRT, right? So I might as well keep this up on the board because we keep coming back to it. But solve this for T. So T is equal to PV over NR. If we put those in here, notice that the NRs cancel. So we're going to get P1 V1 times V1 to the gamma minus 1 equals P2 V2 times V2 to the gamma minus 1. I'll put them on there. It doesn't matter. But now simplify. Okay, well, the NRs go away. Move on. I can combine these V's using the rules of exponents, because that's V to the first. It's also V to the first. So we get P1 V1 to the gamma equals P2 V2 to the gamma. So we'll go ahead and box that as well, because there's a sort of second form of what's going on with an adiabatic process. So we could do the same thing and think about what did I increase the pressure to using this, right? So let's look at that real quick. So we'll go again where that final volume was 1/13 the initial. And if we go with pressure 1 being 1 atmosphere, which definitely wasn't, the pressure here is less than 1 atmosphere, right? Because we're up at elevation. But just for the sake of making life easy, let's just go with that's 1 atmosphere. All right, well, if we put all that stuff in, so we're going to get 1 times V initial. This is now to the 7/5 because it's just gamma. That's going to equal P2 times V initial over 13 to the 7/5. The V initials cancel, and we're left with P is equal to 13 to the 7/5. And let me get that real quick. So if I take 13 and raise it to the 1.4, that's around 36 and change, 36.3. So check that out. Look at how much I increased the pressure in there. 36 times. Now, you guys don't have this in front of you, but if you do this, you push it down. I wonder if I can make it show up here. If I let go, see how it bounced back up? Because the pressure is so great that it wants to expand back. So there's a huge increase in pressure when you do that as well.
Is that why sodas foam when you shake them?
So, okay, so soda's foam, let's see if we can reason this out. This is one that I can't tell you right off the top of my head. So let's just think about what happens. When sodas foam, the gases that are trapped in the fluid are escaping, right? So probably what's going on when you shake up a can of soda is that you're increasing the velocities in the gases, which is then making them want to escape more. But for sure, you're increasing the pressure inside the can because you're getting that gas release from the fluid into the space that's allowed for the air, well, the non-liquid part. So then when you open, it's trying to equalize the pressure, which is why it all comes tearing out. But the actual cause of that increase, I think, is the excitement of the molecules, of the carbon dioxide molecules that are in the soda itself. So that's my best explanation for it.
Or sounds completely reasonable.
But remember what I was talking about before we even started. Don't just take my word for it, right? I mean, I try to be a straight shooter, but I don't know everything.
Yeah.
All right. So there's a second form of what's going on with adiabatic. All right. So then the question is, could we maybe get one that doesn't have volume? Right? Is there another way that we could adjust this or do something? But let's look at the work specifically, because we don't have anything that says work yet. We've seen how P and V and T and how they're all related. But let's actually look at how much work is done. But this one's pretty fast. This one's actually pretty easy. Because again, for adiabatic, since we know that the heat is 0, we know that the change in energy is equal to the negative work. So let's think about the change in energy. Well, the change in energy we saw was equal to N times CV times delta T. So the work is the negative of that. Well, since we've been doing this like initial, final, 1 and 2, let's put those in as well. So that change in temperature, that's actually going to be T2 minus T1, right? T final minus T initial. But we can go ahead and distribute this minus sign. So let's do that. All right, so in an adiabatic process, here's the work that's done. But I don't really want it like this. Really, I want to get rid of the N. N is tough, right? How many moles of gas were in this? Yeah, exactly. I don't know. No clue. So I would rather not have it in terms of how much gas was in there. I still need to know what kind of gas, right? I still need to be able to put in a CV, but at least I can have a good guess on that, right? Like we were talking about, it's primarily nitrogen and oxygen. Okay, so let's take care of that N by using good old PV equals nRT. Okay, so that means that N then is actually going to equal, well, let's do it this way. Let's change the temperatures. Again, using PV equals nRT. So this is going to be P1V1 over nR minus P2V2 over nR. So I can factor out the nR, and the n's are going to cancel. So we get CV over R times P1V1 minus P2V2. And we can do the exact same thing that we did when we had CV and R before. I don't know if you remember that, where we created the gamma by kind of splitting it apart. But CV over R, it's actually equal to 1 over gamma minus 1. And we got P1V1 minus P2V2. So let's put a box around that, because here is one way we can figure out how much work is done. Alternatively, there was this one that involves temperature. But if you really want to get temperature in this, like we can eliminate the P using the V from that other fact that we saw, right? That the PV to the gamma was always the same. Or we could get rid of the V using the T. Like you can just manipulate these equations all you want. But these are now the equations for work. So when it's adiabatic, it's actually a good thing because we know a lot about it and we can figure out, explain why we saw that paper light on fire. All right, so how do we feel about adiabatic? Not too bad? Again,
Not too bad.
it's really mathy, which is probably why I don't mind it, because you just follow the process of the math and we get these relationships. All right. Well, I think we're going to pause here.